Hello, I'm David. I'm one of the lecturers in the Maths Learning Centre, and I was just doing a rough and ready lecture on using derivatives to sketch graphs, and I ran out of time, so I'm going to do a couple more examples now. So first I'm going to finish the example I started in the previous lecture that I ran out of time to finish. And it was sketch the graph of y equals 2 minus 3x minus 4 over x minus 5, including all x-intercepts, turning points, and inflection points. Okay, so the very first thing that I talked about in the previous seminar, there were 4 features that we want to talk about. It's not mentioned here, but I do have to talk about where the function is undefined first. So y is undefined when any part of it that is a fraction when the denominator is 0. So when x minus 5 is 0, that means that when x is 5. And there will be a vertical asymptote there because the numerator isn't 0 at the same time. Now I can look at this and attempt to figure out whether it's going up or going down next to that asymptote, but that's going to be covered by the bit when I figure out where it's positive and negative, so I don't actually have to do that now. So what I'm going to do now is I'm going to figure out when y is positive and negative. And along the way I'll find the x-intercepts. Okay, so first I want to solve. I always write the L when I do solve. I'm going to solve y equals 0, which means 2 minus 3x minus 4 over x minus 5 is going to be 0. And so at the moment the most annoying thing is the fact that x minus 5 is on the bottom. So I'm going to multiply it by x minus 5. And this does not look fun, so I think I might expand it out. 2x minus 10 minus 3x squared plus 15x, and then minus 4 is still there. I'm just going to rearrange that, 3x squared, and then there's a 2x and a 15x, and there's a minus 10 and a minus 4. And I'll feel much better about this if I do this. Okay, now it doesn't look fun to factorize that, so I'm just going to use the quadratic formula. So x is equal to, now if this was a here, and this was b here, and this was c here, minus b, which would become a plus 17, plus or minus b squared, minus 4 times a times c over 2a. Okay, that's a 6. So let's see, what have we got? 17 squared. The minus isn't going to make a difference when I square it. 121. Oh, that's cool. 121 is a square number. So that'll be 17 plus or minus 11 over 6. So the bigger one will be the plus, so 17 plus 11 is 28 over 6. 17 minus 11 is 6, so this will be 1 and 14 thirds, which is approximately a little bit under 5. 4.0 667. Okay. All right, so the 3 points, 3 places on the x-axis we've seen so far are a place where it's undefined, which is x equals 5, and a place where 2 places where it's equal to 0. So I'll put them all on a sign diagram. For y, so the x things that I have were 1 and 14 over 3 and 5. So 5 it was undefined, and these 2 it was actually 0. So I have 1, 2, 3, 4 regions that I need to check. Now I can't do f of things because I haven't been told what f is, so I'm going to have to do it with y. So if x is equal to something less than 1, so 0, y is equal to 2 minus 3 times 0 minus 4 over 0 minus 5. And so I've got minus 1 and then plus 4/5, which is still negative. I just want to check that. Oh, no, it's not. No. It's positive. Because 3 times 0 is 0, not minus 3. So 2 plus 4/5 is definitely positive. It's easy to fix. Something between 1 and 14/3 is 2. 2 minus 3 times 2 minus 4 over 2 minus 5. So that's minus 4 plus 4/3, which is still going to be negative, which makes sense. If it should cross the x-axis properly there, I reckon. Something between here and here, I'm just going to have to go 4.8. This one I decide that I'm going to do on my calculator. So we have 2 minus 3 times 4.8 minus 4 divided by 4.8 minus 5, which is 7.6, which is positive. And then over here at above 5, let's go 6. So I've got 2 minus 18, and then this 6 minus 5 is positive, so that's minus another thing, so it's definitely negative there. Okay. So I can also tell based on this which direction my graph is going to be going, and I'm going to just add that to my diagram in a different colour. Since this asymptote here, it's positive here, it must be going up, and since it's negative, it must be going down. Okay. All right. So we've figured out where it's positive and where it's negative. It's above the x-axis here, below here, above here, below here. We figured out what it's doing next to its asymptote. The next thing to do is to try and figure out what's happening with the increasing and decreasing. Now I'm assuming that across here it must be decreasing somewhere because it's going from positive to negative. And across here it must be increasing somewhere because it's going from negative to positive. So I assume there's going to be a turning point in there somewhere. There's nothing stopping there being a turning point here because it could be negative for the whole thing. And in fact it's going to have to be negative for the whole thing. This is never going to cross the x-axis again, so it's negative forever here. So it's probably, I'm guessing it's going to come down again, but I don't know for sure. Okay. Okay, so now let's do the increasing and decreasing. Y was equal to this to begin with, 2 minus 3x minus 4 over x take 5. And I want to differentiate that to figure out where it's increasing and decreasing. So it probably is going to be easier to write this like this. So dy on dx would be the 2 will go away, the minus 3x will just become a minus 3. That minus 4 will still be attached. I'll multiply by the current power and put the power down by 1, and then I'll multiply by the derivative of this because the chain rule and the derivative of that is 1. Okay, so we've got minus 3 plus 4 x minus 5 to the minus 2. And I guess a power of minus 2 is the same as dividing by it. But I'm just going to leave that there the way it was and write it separately this way. Okay. All right. So I want to solve for when dy and dx is 0. So minus 3 plus 4 over x minus 5 squared is 0. Now I do see only one x there. So since there's only one x, I can just do moves where I keep progressively removing things from where the x is until the x is all by itself. So I don't want that minus 3 there. It's the furthest thing from the x, so I'll move it first. The fact it's on the bottom is bad, so I might just do this. Multiply this and this by x minus 5 squared. And then 4/3 is x minus 5 squared, so I can do the square root. I'm just going to simultaneously switch it around. And so x is 5 plus or minus the square root of 4/3. Okay, but just a reminder, y is undefined at x equals 5, so I'm going to have to think about that. Let me just do an approximately equal to this. 5 minus the square root of 4 divided by 3 is 3.8-ish. And 5 plus the square root of 4 divided by 3 is 6.15-ish. Okay. All right. So that's given me 3 points that need to be interested in when I draw my sign diagram. Okay. So I've got x, I've got dy and dx, and the biggest point I have is 6.15-ish, and then 5, and then 3.85. So I've got 4 zones, and it's not defined there, and it's 0 there, and it's 0 there. So let's see. I can choose any number on this side, so when x equals 0, dy and dx is minus 3 plus 4 over 0 minus 5 squared. And like 4 over 25 is a nice small number, so it's not going to get positive, so it'll be still negative there. And between here and here is 4, I can do that. Okay, minus 3 plus 4 over 4 minus 5 squared, which is going to be positive, because 4 minus 5 squared is 1. So it's plus there. 6 will work because it's actually in that zone. Minus 3 plus 4 over 6 minus 5 squared, which is still positive. Interesting. Very interesting. I'm interested to see how that lines up with what's going on here. So it's increasing after 5. Oh yeah, and I'm guessing it's going to be decreasing again, because if it just kept increasing forever, I mean, I guess you could increase and still never reach the x-axis, so we'll see what happens, eh? And when x is equal to something beyond 6.15, we get minus 3 plus 4 over 7 minus 5 squared, which is negative. Because this is like 2, and 4 over 4 is 1, and so it's still negative. Okay. Well, that makes sense. Okay, that matches up with what I had before. So it's decreasing, increasing, increasing, decreasing. These are both turning points. The derivative, the function doesn't actually exist there, so that's not a turning point. Okay. So just back before, I probably should have actually explicitly listed that the x-intercepts are at x equals 1 and 14 over 3. And I did already say right at the beginning that there was a vertical asymptote at x equals 5. Okay. So I should actually figure out what these turning points are. So when x equals, it's not technically actually 3.85, but I really don't want to sub this into the function. Actually, it's not too bad, because I know what x minus 5 is. I reckon I can sub them into the function directly without using decimals. Oh, that's going to be cool. I love it. So we have 5 minus root 4 on 3, where the y is equal to 2 minus 3x. No, I can't be bothered. So 5 minus square root of 4 divided by 3. And then I'm going to go 2 minus 3 times that answer, minus 4 divided by that answer. I still got the answer there? Yeah. 2 minus 3 times that answer, minus 4 divided by that answer, minus 5. So y is approximately minus 6.072. And if x is equal to 5 plus root 4 on 3, which was approximately equal to 6.15, y is approximately equal to, so what was it? 5 plus the square root of 4 divided by 3. Okay. And then we go 2 minus 3 times that answer. 2 minus 3 times that answer. Minus 4 divided by that answer. Minus 5. Wow. Really? There you go, 19.928. That's really far down. Wow. Okay. Good-o. So the turning points are approximately 3.85, 6 minus 6.07, and 6.15 minus 19.928. So I just want to check something there, because the fact that that's negative is bothering me a little. Let me just go back here. The 3.85 is in here. Oh, and it is going down, and then it's going to turn and go up again. Okay, cool. Just making sure. All right. So now I want to do the concave up and down. And so I'm going to need the second derivative, so it makes sense for me to write down the first derivative in a way that I can use. So the second derivative, which is sometimes written as d squared y on dx squared, you would see it as f double dash sometimes. The 3 will go away, 4 times minus 2 times x minus 5 to the minus 3 times 1 because of the chain rule. So I get minus 8 over x minus 5 cubed. We'll solve d squared y on dx squared equals 0. So minus 8 on x minus 5 cubed equals 0. And multiply both sides by x minus 5 cubed, and I get minus 8 equals 0, so there's no solutions. Okay, so there's not going to be any inflection points. but also y is undefined at x equals 5, and so that's going to cause a sign diagram to be necessary still. And even if it wasn't, even if there was no inflection points, we would still draw a signing diagram and draw a big plus or a big minus. So a sign for d squared y on dx squared. This is the x, this is d squared y on dx squared, and there is 5. That's the only point that we're interested in. And so when x is less than 5, let's say 0, then this is minus 8 on 0 minus 5 cubed, which is minus 8 on negative number, which is positive. And when x is equal to something more than 5, like 10, d squared y on dx squared is going to be minus 8 on 10 minus 5 cubed, which is the same answer but negative. Okay, so it's concave up here, it's concave down here. If this was a point where the function is defined, it would have been an inflection point, but the function's not actually defined there. Okay, and so I'm just making sure I don't lose any of my writing. So let's summarize this. What have we got? We've got various points of interest. Our points of interest are 1, 14/3, and 5. And we should write them all down. So, okay, so I'm just going to summarize everything and put them down on the same page again. So we have X-intercepts. So I'll sum up. X-intercepts were the points 1, 0, and 14/3, 0, which is approximately 4.670. So that's the x-intercepts. So there's 2 of those. Okay. The turning points. I'm just going to put them underneath each other so it's easier to see what's going on. So my turning points were at 3.85 minus 6.07 approximately, and 6.15 minus 19.928 approximately, and there were no inflection points, but we did have a vertical asymptote at x equals 5. Okay, so that's all the information we have. So let's draw it. So most of the action happens over here on this side. So 1, 2, 3, 4, 5, 6, 7. You know what? There's not enough room to draw a really good graph here. I'm just going to draw a little picture here just to make sure that I put my asymptote directions correctly, and it sort of goes up on this side and down on this side. Okay. Okay. One, 2, 3, 4, 5, 6, 7. So the x-intercepts are 1, 0, and a 1, 2, 3, 4.6 there. All right. I shall call this point A and this point B so that I can label my graph. Okay, 3.85, 1, 2, 3, 4. No, yeah, that's 4 there. 3.85 is about here. Let's call that point C. And 6.15, 1, 2, 3, 4, 5, 6.15, so it's about here. Let's call that point D. Okay, there's an asymptote at 5. 1, 2, 3, 4, 5. I do know it goes up here and down here. Okay, all right. Let's just see. Oh, the C isn't actually at that point, though, is it? That's the x-coordinate of the point. The actual coordinate of C is at minus 6.07, which is about, we don't have to have the scales on the same axes. Let's call that C. If that's about 6, then 19 will be about 3 of those, which would be about here. Okay. Right. Okay. Glad I gave myself some space, eh? Okay, so I know that it's positive here, it's negative all the way to here, and then it's positive here, it's negative all the way to here, and then it's positive again. Okay, and then it's negative for everything here. Okay, and then it's decreasing here, decreasing all the way to here and increasing here. Okay, and it doesn't have any inflection points. Okay, so it's always concave up here and concave down here. All right, cool. So this is going up, and after point B, it's still going up after point C, and then it will go up there like that, and it's still going up here. And I did actually figure out what the y-intercept was. I'm just going to pop that in. It wasn't actually asked for, but I'm going to put it in because I did actually calculate it way back here. Where is it? X equals 0. That would be 2.8. Okay. Which is about here. I will just say that that's 2.8 there. So 0, 2.8, and I will call that point E. Okay, and then this, it's concave down everywhere here, and it's increasing in that bit and decreasing in that bit. So it can't go down too quickly because there's not another asymptote, so it's got to go out that way. And there's my graph. Okay, it would be really cool if it really turned out this way when I drew it on Desmos. Oops, sorry. Yeah, let's turn these off. So what was my function again? 2 minus 3x minus 4 over x minus 5. Yep, there it is. And look, it's about 19. It's about minus 6. It's doing exactly what it was. And let's just draw in the x-intercept, x-asymptote. Yep, there we go. Sweet. Beautiful. I was able to do it. I guess the only other thing on this graph that needs to be done is to say that, label it somewhere as the graph of y equals 2 minus 3x minus 4 over x minus 5. Okay, well, let me do another example. This time I'll do a polynomial. I'll do it as a y as well. So let's see. Sketch the graph of y equals x plus 2x minus 4 cubed, showing x-intercepts turning points and inflection points. Okay. Well, it's always defined. So I don't have to worry about the annoying extra point there that I have to keep considering all the time. And it's, first I guess we'll figure out when it's positive and negative. Okay, so we're going to find out when it's 0. And it's already factorized for me, so that's convenient. So we have x equals minus 2 and x equals 4. Okay. And then I'll do a sign diagram. For y. So there's x, and this is where the y's are going to be. So I've got it minus 2 and 4. So when x is equal to something below minus 2, so negative 3, y is negative 3 plus 2, negative 3 minus 4 cubed. Now that's a negative number, because it's negative 1. That's a negative number, and when you cube a negative number, it's still negative. So negative times negative is positive. And when x is equal to 0, y is equal to 0 plus 2, 0 minus 4 cubed. So 2 times minus 4 cubed minus 4. Got to use the correct minus. Minus 128. Wow, negative. And when x is equal to, say, 5, y is equal to 5 plus 2, 5 minus 4 cubed, which is positive. Okay? So it's below the x-axis here, above the x-axis here, below the x-axis here, above the x-axis here. All right? And that's about the right thing. This is a quartic. It's going up because of the positive, when I expand it out, there'll be a positive x to the 4. So, you know, it's doing the right things on that front. Okay, and the x-intercepts, while I'm at it, are at minus 2, 0, and 4, 0. Now I actually know what shape it is. This is a cubic, so it should be shaped like a cubic at the place where it crosses the x-axis there from my knowledge of how polynomials work. All right, let me do the increasing, decreasing. So first I'll need to find the derivative. So y was equal to x plus 2x minus 4 cubed. So dy on dx, I reckon product rule will go. It's probably not worth expanding it out. So x plus, I'll differentiate the x plus 2, which will give me a 1. And I'll keep the x minus 4 cubed. And then I'll keep the x plus 2. And I'll differentiate the x minus 4. So that'll be a squared and times by 1 because of the chain rule. I want to put brackets around that so it's more obvious where that came from. And so that's x minus 4 cubed plus 3x plus 2 times x minus 4 squared. And I notice that there's an x minus 4 squared in both of these. So I might just factorize that out. Because I'm going to have to factorize it eventually in order to solve when it's equal to 0. X minus 4 squared, x minus 4 plus 3x plus 6, x minus 4 squared, 4x plus 2. Okay, so now I'll solve for dy on dx equals 0, which means x minus 4 squared 4x plus 2 equals 0. So either we get x minus 4 squared equals 0, or we get 4x plus 2 equals 0. And this would be that x is 4. This would be that 4x is minus 2, x is minus 2 over 4, which is minus a half. Okay, so if I have turning points, that's where they're going to be. They might not actually be turning points. I can't tell yet until I find out where it's increasing and decreasing. So let's do a sign diagram for dy and dx. So what was it? Minus a half and 4. So something less than minus a half would be minus 1. And at that point, dy on dx would be, what was the formula for it? X minus 4 squared 4x plus 2. So this is minus 1. 4 times minus 1 plus 2. Okay, so that's squared, so it's positive. Minus 4 plus 2 is negative, so that's going to be negative. So that's negative. When x equals 0, dy on dx is, because 0 is between these two, and we get 0 minus 4 squared 4 times 0 plus 2, but that's positive because it's squared, and so we get positive. And when x is equal to 5, dy on dx is 5 minus 4 squared 4 times 5 plus 2. Well, that's positive and that's positive as well, so it's still positive. Okay, so we don't have a turning point here. It's not a turning point. And so we will say my turning points, I have x equals minus a half, where the y will be equal to minus a half plus 2 minus a half minus a quarter square cubed. Oh gosh, so 2 minus a half would be 1.5, which would be 3 over 2. 4 plus a half would be 4.5, which would be 9 over 2. And that's going to be a terrifying number. 9 cubed, 3 times 9 cubed is 2,187. Over 16. Wow. 136.6875. That's actually literally equal to that. Okay. Cool. So turning point is minus a half 136.6875. Wow, that is a very high turning point. Oh, no. When you cube things, it'll be negative. I was worried about that because I'm going, how can it be high if it's coming down to it and then going up? So it's really low. So it comes down, goes down really far, and then comes back up again as it gets to the 4. Oh, and actually I know what's going... Oh, no, I don't. It comes back up again. And it's 0 at this point because of over here. And then it keeps going up after that. Okay. So next bit would be concave up and concave down. Okay. Okay, so I'm going to need the second derivative. So I'll start with the first derivative, which was there it is. X minus 4 squared 4x plus 2. And it's important for me to write that down so the person reading it doesn't have to remember what it is, so that they can figure out how I did my derivative. So the second derivative 2x take 4 times 1, that's the derivative of that first bit, and then I'll keep the 4x plus 2, and then I'll keep the x take 4 squared and differentiate this bit, which would be 4. I guess that's an x take 4 times 8x plus 4 plus 4, lots of x take 4 squared. They've both got an x take 4 in them, so why don't I pull that out? 8x plus 4 plus 4x minus 4, x minus 4, 8x plus 4 plus 4x minus 16, x minus 4, 12x. Really? So 2 times this is definitely 8x plus 2. And we're left a 4 bit behind, and it was 4x minus 4 left behind. So we get 8x plus 4x, yep, and we got 4 minus 16. Oh wow, cool. So we get a whole number. Sweet. That's so beautiful. Okay. So we solve d squared y and dx squared being 0, which means that we'll get 12x take 4, x take 1 equals 0. Which means we're going to get either x is 4 or x is 1. Okay, so let's do my sign diagram. No, not enough space. Let's do it on the next page. Sign diagram for d squared y on dx squared. And so we've got x's, we've got whether d squared y on dx squared is positive, and we have 1 and 4, so there's 3 places to test. So when x is equal to 0, d squared y on dx squared is, where was the formula? Here it is, 12 times 0 minus 4 times 0 minus 1, and that's negative, negative times negative is positive. Let's try something between 1 and 4, let's try 2. 12 times 2 minus 4, 2 minus 1, that's negative this time because that's negative and that's positive. And I'm guessing that the next one is going to come out as positive for that same reason. Now these are both positive, so it's a plus. So it goes from concave up to concave down to concave up. So this really is an inflection point because it switches from concave up to down, and this really is an inflection point because it switches from concave down to up. Okay, so inflection points, we're going to need to figure out their y coordinates. When x equals 1, y is, now what was the original function again? There it is, 1 plus 2, 1 minus 4 cubed, which is 3 times minus 3 cubed, which is negative 81. Beautiful. And when x equals 4, we actually already figured that out. That was 0, because x equals 4 was one of my x-intercepts. And so the inflection points are 1, 4, and 1 minus 81, and 4, 0. All right, so I think I have all the information I need, except possibly it doesn't have any asymptotes because it's polynomial. Beautiful. So I was just going to summarize all of that. So to summarize, x-intercepts, we have minus 2, 0, and 4, 0. The turning points, we have minus a half, minus 136.6875, and inflection points I have 181 and 40, and I did figure out the y-intercept along the way there. It was back here. No, the x will be 0 at the y-intercept, and the y value came out to minus 128. Okay, and that's everything I need to know, except the sign diagrams will tell me which way up everything is. And I might give these names. Let's call this A, and this B, and this C, and this D, and that's B again, and this E. Okay. All right. Scale on this axis is going to be really interesting. Mostly everything's, is that a plus 81? Negative 81. Mostly everything's negative, so I'll just draw it here. So my x-intercepts are at minus 2, 0, that's the point A, and at 4, 0, 1, 2, 3, 4, that's the point B. And I don't know where to put that at the moment, so it's not in the way of the function. I don't really know, but I'm assuming it's going up here. So, and it's positive here, and negative here, and positive here. Okay, and then the turning point is at minus a half, minus 136. So let's just. About there. Okay, that's the point C. The point D is at 1, negative 81. So there's 1. 81. It's about 2/3 of the way there. That's the point D. There's an inflection point there too. And the y-intercept is at 100 minus 128, which is about there. Okay, so let's see, it starts being positive, and then it switches to negative here, and then as we move along, it's decreasing until it gets to minus a half, which is this point here. So, yep, so now it's coming down here, and over on this side, it's concave up. So it's supposed to go concave uppy. So it's not allowed to turn this way because it has to be concave up. Okay, so that's that bit. And then between C and E, so after the turning point here, after this turning point, it is increasing, and it's still we're not up to 1 yet, so it's still concave up. And D is the place where it stops being concave up and starts being concave down. So it's going to go like that way. Okay. And then it's still concave down, and it's still increasing up to here. Still increasing and concave down. And actually, the derivative is 0 here, so it has to flatten out there. The slope has to be 0 at this point. And then it's still increasing here, but now it's concave up. Right. Beautiful. That's how to do it. So let's just look back at some things that I did there. So in both of them, I slowly worked my way through the positive and negative bit, which allowed me to find the turning points. Positive and negative part. And then I had the increasing, decreasing part, where I did the first derivative. And then I had which allowed me to know whether they were turning points or not. And then I had to find the y-coordinates of those turning points. And then I had to do where it was concave up and down. And then I had to find the y-coordinates of those inflection points. But it turned out that sometimes you don't get an inflection point. And then you're able to combine all that information together to make the graph. And the easiest way I find is to label all the points with letters so that the person reading it can go and look up what they are. So, some details about the way I wrote this. I was very careful to say which piece was which. I gave some headings. And I was very careful to say what I was doing. I'm going to solve when this is 0, and then I'm going to actually do the equation solving. I didn't write at any point A, B, C, because technically, if I wanted to write them down as part of the actual working, I would have to say what they were. So I didn't do that. And every time I figured out a decimal, I said it was approximately equal to. Probably should have said how many decimal places I did, and I probably should have been consistent as to how many decimal places I did. Sorry about that. And I did the sign diagram, and every time I did a sign diagram, I told people how I was calculating it. You'll notice that it's okay to say the x-intercepts are at a location. It's also okay to say what the points are, the coordinates of the points are. And look at this. When I did the derivative, I did y equals, did some stuff, and then I did dy and dx. And every time I calculated a derivative, I wrote the thing before it so that the person reading it would know what's happening. And every time I did a sign diagram, I told the reader what it was a sign diagram for. And that's all important stuff for actually showing your working for these kinds of problems. All right. Thank you for listening, and I will stop it there.